My name is Bly, Dr. Bly, and this is Chem 101, first semester chemistry lecture part. We'll cover the lab afterwards. And this is the routine. Sign in when you come in, and I'll have handouts here. Usually won't be this many. It's just the first day thing. But you got copy of the syllabus. You got a copy of my schedule that shows you where I'll be, when I'll be there. You may want to pay attention to the dark red ones with yellow highlights. Those are my office hours. And the Zoom idea. When I do office hours, I always Zoom them too. So if you can't come to campus, you can meet me with a Zoom. Now those office hours are there to satisfy management. We have to have 10 hours of office hours a week. But anytime you need help, all we have to do is arrange a meeting, either in person or by Zoom. And I'll always use that same ID. That's my personal ID that I use for Zoom. Except for Mondays. Mondays I don't have in person because I Zoom late, so I Zoom from home. But barring any complications or family problems or management yanking me out of my chair, that's where I'll be at any given time. The other things we'll get to, as we go. All right, so let's take a look at the, I'll tell you what, everything that I give you in class is duplicated in Brightspace. So if for some reason you can't make it to class, you may pull an absence, but at least you'll have access to the material. And I'll show you where everything is in just a minute. I've been doing that from the beginning, putting everything in the learning management system, even if it's not a web-based course or a Zoom course, or one of those other types. So you'll always have access to that material. So let's, has everybody been into Brightspace and you kind of know your way around? Yeah, I see a few nodding heads. So I'll go in there, but I won't linger except on things that I really want to make a point of. So what you want to do is go into my new rigor. It might look a little bit different than I probably have more things than giving you, but you just go to D2L, which is Brightspace. And that opens up the landing page for Brightspace. And this waffles place I like to go to find my course. Just click that and find the course. This is ours. 26612 is the CRN number. And that I'm gonna stay over here for a minute. I like to be over there, but my magic wand doesn't always work. A little nondescript welcome. I want to call your attention to this also. Barry Pine is one of our staffers who has a background in sciences and mathematics. He does tutoring for the school. And that's his contact information, the hours that he'll be available here Sunday, Monday, and Wednesday evenings. And then that's his Zoom ID. So does everybody know how to use Zoom outside the classroom, how to connect your Zoom? You can do it on your phone, you can do it on a laptop, you can do it on your, I don't know if you can do it on a Chromebook, but I think so. Use that ID and you can connect with him at any of those times if you're having trouble, you can't get in touch with me. Or if you're just tired of me and want to talk to somebody else. Okay, so when you get ready to access the materials in the course outside the classroom, the content is where you want to go. These others tabs on the mini bar access some interesting things like grades and assignments. Probably find homework assignments there. Oh, I better change to a student so it looks more like what you're expecting. Okay, so this is what it will look like for students. All right, so if you go to content, then you get, here, go back to the top. Some of these things over here, in fact, most of them they're mandated by the school. So I didn't put these in here. They were changed. I think they're just links to different pages. You may already know that. But for the course content, go start here, lessons and resources. Okay. And then if it's expanded, you can just collapse all and then go down. It's a little easier to manage. That's a little blurb about me. Here's the syllabus. And in here, you'll find the syllabus, you'll find my schedule that I just handed out, and you'll find this is a Zoom link to my office hours. So let's look at the syllabus. We'll do that. And so goes up a little bit, so we get a better picture of it here. Okay, I'm going to try this thing out. See if I can talk on camera. Helps if I turn it on. Okay, all my contact information is here on the left-hand side. Let's see. What's not going to do? Sorry, I'm going to have to go off camera again. Okay, all my contact information is there, and believe it or not, my cell phone is in there. Best way to contact me on the cell phone is to text. Then if I'm driving it, I'll crash the car. But you can call the office, and I may be there. If I'm not there, leave a message. The system we've got will transcribe audio messages. Actually, it will transcribe it. It'll take the message and put a link in an email and send it to me. So I get them pretty quick. Either way that you want to contact. Let's see. Required text. You don't have to buy a textbook, but you do have to buy CHEM101 Unlimited, which gives you access to the ebook and homework. Now, if you're going to stick around, is this most of you guys in NLT? Okay. Everybody? No? No? Okay. Well, that's fine. I just wondered if you're going to take 102, 104 within a year from today, or from the day you purchase, you can buy one semester and that'll just get you the spring semester, and then it's over. You have to buy it again if you want to get into second. But if you're going to take the second in the summer, the rest of the series, then just buy the whole year, and that'll give you access, and it's more cost effective. I put the prices here. These are current bookstore prices. So if you go into our bookstore, that's what they cost. And be sure when you buy it to buy it using your New River email address, because when you go to register, the school is the licensed entity and you're a user. So if they don't see your New River email in newriver.edu, then you may have a little trouble registering for this particular product. And I'll say a little bit more about that in a minute when we get to it in Brightspace. So you don't have to buy the hard copy, and unless you just like the feel of paper. But there are the particulars. If you want to buy the hard copy, there it is. Since it was published in 2018, I bet there are a lot of used copies out there floating around. Cheap back to the cheap if you'd like the hard copy. But if you're all electronic, then you get the ebook. And the nice thing about the ebook is it's searchable. So once you go into the ebook on the Cengage website, you can just find any topic you want. Okay, course materials you're going to need. For the lecture part of the course, you're going to need a calculator, scientific calculator. I put the functions in here that you're going to need to complete the course, but if the package says scientific, it'll have everything. Got one here. I keep a spare. My calculator is reverse Polish notation. Anybody ever heard of that? No. It takes some getting used to, but it's more efficient than algebraic, where you have to put in parentheses and maybe you have to do a sub-calculation and then use it. But I keep an algebraic calculator here in case you run off one morning and forget your car keys and your calculator, and you're just in a hurry. So you don't have to learn how to use mine. But you need that calculator, and you can get a sufficient calculator at Walmart for $10 or less to do the job. But you have to learn how to use it yourself. We don't have time to do this. You have to use every different type of calculator that's out there. And you need that calculator when you're taking exams. Can't use your smartphone calculator because of that word that's smart. Phones are really smart, and they're. But I had a student use one cheap, so that's okay. I guess that's one rotten apple spoils it all for everybody. So you have to have a separate calculator. You can't use your smartphone calculator. Exams. You can use many other times. No problem. Okay, so you need that. If you're I don't know if I want to. What I'm toying with the idea of making exams available on Brightspace, but if I do that, I've got to enable lockdown browser response. Have y'all used that before? Okay. I'm not sure if I'm ready to do that because my paper exams I don't think they've been completely transferred into the Brightspace environment. So it'd be a lot of work getting my things in it so that you can take it as Brightspace. But I have another option, and I'll talk about it if we need it. If for some reason you can't make it to class on exam day, then call me and we'll work something out. So this little blurb here on the lockdown browser, sort of set that aside for now until I make it available. This other stuff is useful information, but I'm not going to dwell on it. We're going to get down to the important things like exams and homework. When you register for homework, I'll show you where that is in Brightspace. You have to register from within Brightspace. You gotta click the link there. If you don't, because Brightspace and my Cengage homework app are linked, then if you went outside Brightspace and registered, the results of your work would not show up in Brightspace. So you got to go through Brightspace and register that way, and then they're linked. So what's it all worth? Well, there's your grading scale. The chapter exams are worth 57%, equally weighted, and there are 7 chapter exams. And the final exam gets 13%, which is roughly twice as much as the chapter exam. Homework's worth 20% total, and then you get credit for showing up. How about that? All you have to do is just show up and participate. Don't sleep through class. I'll count that as an absence. Or if you spend the whole class texting on your phone, that's absent too. You got to be here and participate. At least pay attention. And the grades, if you want to see your grades, I'll show you where that is in a minute. They're in Brightspace also. Your homework automatically shows up there because
the Cengage and Brightspace are linked. Exams, I put those in manually. And then I take all those grades and I put them in a spreadsheet that is more flexible than the grade book Brightspace. It's kind of a black box. You really don't know how it does it. So I don't trust it. I put all your grades into a spreadsheet and I weight them appropriately. Sometimes I make adjustments depending on how the semester proceeds. And then I put a final grade manually in Brightspace and update it periodically. So how do you know the grade is current? Well, you look at the other grades in the list and say, well, wait a minute, we had this exam today and that grade's not in there yet. So you know that the average doesn't include that grade. And so all the grades that are actually in there, the separate grades, go into the final grade that the average grade that I post. And then there's some extra credit. I've got two of those things that are extra credit. And let's go to the, let's go to here. That's not highlighted. That's not. This is supposed to be, I'll have to update that. The homework and exam day due days, they're supposed to be highlighted in yellow. Are those copies highlighted? Okay, I need to make a change in Brightspace. Anyway, this tells you what we're going to do on what days. Like today, when I get finished blabbing on about class business, we'll talk about chapter 1, chemical foundations. And we might bleed over a little bit into lab time, but that's customary. And then next Thursday, we'll get chapter 2. Oh, that reminds me. If you signed up really early, the schedule probably said the labs were on Thursday. Remember that? Okay. And then we had to change it to Tuesday because there was an overlap with another class that was at lab time. And I checked everybody's schedule to see if there were any conflicts with classes, and I didn't see any. But I wasn't able to check things like family obligations, work schedules, and things like that. So right now would be a good time to find out if moving the lab to Tuesday has jeopardized anybody's work schedules or family problems.
So the lab is from 2 to 3:50 today?
Yeah.
Okay, and it's not 2 to 3:50 on Thursday anymore?
No.
Yeah, I didn't see that.
Okay. So where was I before I interrupted myself? Okay, so you'll notice that actually I can't bring up both syllabi for the lab and lecture, but this is a good time to explain. Whenever there is an exam, let me look to be sure. I don't want to speak. Okay, so that first exam is on the 26th of January. Wait a minute. Oh, okay. That's a no-brainer. Right? Looks like all the exams I've placed on Thursdays. Okay, so there won't be any lab interference there. You just do the lab, do the exam, and you're going. We won't do anything else on that day. Okay. So you can take the whole, what is it, hour and 15 minutes? Yeah, 12:30 to 1:45. Yeah, hour and 15 minutes. So I've got 50 minutes, 49 minutes left. Okay, stop me anytime if you have questions. If you don't, I'll just keep rambling on. But I've set aside time for lecture, and then we have a review day in here scheduled right before an exam. And what we'll use as our guide for the review day is this document. This one says Exam 1 Review. Notice it's set up, it looks exactly like an exam. It's got multiple choice questions and there are a lot of, the exams won't be this long. The reviews are long because I want you to have a lot of practice. Work as many of them as you can. If you're limited on time, then work every other problem so that you get to the end. And that gives you an exposure to all the types of problems because they're duplicates. And then if you want to, some of my students like to sit down and take this as an exam. Just go through. Well, how do you know what the answers are? So they're in Brightspace. There's another document that I used to print out, but I stopped printing it out because I broke the printer one time. I was printing too much and then it overheated. But if you find that you missed a question and you can't figure out why you missed it or how to work it correctly, then I've got this other document in my handwriting. Actually, I took great pains to make it legible. That will show you how at least one way to work the problem. And maybe something will click and you'll see. If you still have problems, bring those questions to class on review day. And we hit those first. Before I start talking about anything else, we'll cover the ones that are giving you trouble. Okay, that's what the review days are for. All right. So we're going to have 5 exams. And let's see, I put in some extra stuff in here, like this Monday is the last day to add drop, 23rd of January. And then here's the spring break in there. And that Monday is when midterm grades are due. So you'll have 4 exams and homeworks associated with them go into your average. So that should give you a pretty good idea of where you stand. It's not like take one. Sometimes some instructors only have 1 exam. And that's your midterm grade. But I like to break them. I have lots of opportunities to succeed. And then I've got set up for that last week before exam week. We have 2 days to review for the final exam. That's so that we'll have enough time to cover all the material. Okay. So we have other policies in here that all you have to do is read yourself. Let's see. If you're going to take the exam face to face, I mean, dressing properly is no brainer. If I'm able to enable the respondus option, then you'll need to dress for that too, because you're going to be in camp. You've probably heard that before. Let's see. There are my office hours. This is stuff that we have to put in. And then we got some appendices back here. This is for registering out homework. How to do that. I'll show you where that is in Brightspace in just a second. And then this is a good place to stop right here. When you're registering for the Cengage and the OWL homework, if you run into problems, Cengage has set up some office hours until 17th of February. And you can contact them, just click on this link right here. And it'll get you IT support. You don't have to go through their phone maze to get help. You go straight to that link and there'll be somebody there to help you. Or there's a telephone number there also. I thought that was a nice thing. There's also, I'll show you later. There's also contact information for their sales rep, and she's really good at solving problems. Is it in the syllabus? Or did I just, maybe I just put it in again. In Brightspace, I think that's what I did. Name is Dee Frederick. Anybody talk to Dee Frederick before? Okay. She's a nice lady. She knows what she's doing.
This is the thing on the responders and lockdown browser. We won't need that unless I enable that option. But I put it in there in case we did. And then do I have another one? So, attending Zoom class. Okay. You guys probably already got that. There's this thing, if you have to attend by a Zoom session, this side-by-side mode is good to have. Then you can increase or decrease my side and increase the shared slide side. And so that won't be much help in this class because I don't share slides in this class. They're up there on the board. But I do record everything that happens in the class, at least within earshot and within camera range. And after class, Zoom sends me the raw footage, and then I reprocess it mostly for video quality. And if I have any embedded videos, it's like a recording of a recording is pretty bad. Right? So you can see it here okay, but when I repost it, I insert the original video. And then after processing, I upload the video to my YouTube channel. And then in Brightspace, I put the link for that particular video. And there's several of them in there already, right, from previous semesters. I never throw anything away. But that way, you can go back and look at the video. If there's something you thought you might have missed, and that's very common. The average is for anybody who's sitting, listening to somebody talk or seeing a presentation, you miss about half of it, even if you take good notes. So this is one way that you can go back and fill in the gaps. Or if for some reason you can't make it to class, you've got the video to watch. Of course, it's not as easy to miss a lab. Right? That's all hands-on. So if you miss a lab, then you have to depend on your lab partners for the data. Otherwise, you can't write the report. Okay. That's the end of the syllabus. Now let's go back to let's go to the top. There's let's go back. Notice the breadcrumbs. You can walk back stepwise. I'm going to go back to start here. Show you the rest of the format. I think you've already seen this. Have you been perusing? Okay. There's where you help register your homework. It won't do me any good to click the link there because it thinks I'm a student and it'll just shut it down. There's my office hours. Let's see. There's your ebook. These are some supplemental documents. We're not going to spend time there because they're not absolutely necessary. This is where you find your class meetings, Zoom class meetings. In this one. And then everything else is in modules, and each module represents an exam. So module 1 would be exam 1. And they're all set up the same way. So I'll just go into one of them and show you what it looks like. Okay, we got objectives there you can look at. You notice the PowerPoints come in 3 flavors. If you have Microsoft PowerPoint, you can view the file this way, or you can look at the PDF file, which it won't have the animations, it won't have embedded videos. But if you're desperate, you can look at that one on your smartphone. This one's a nice one, HTML5 format. I take the PowerPoint slides and use a program that takes everything, including animations and all the embedded videos, and puts it into one place. You don't need PowerPoint to watch it. You just click on this. And then you can step through the slides like that. And that's the one we're going to look at just a little bit. And there shouldn't be any animations in this one. Okay. Also, let's see, let's go over here. Good, go module 1. We can get at it 2 different places. There's chapter 2. So chapter 1, chapter 2 are in exam 1. And what we're going to cover in chapters 1 and 2 includes learning the vocabulary. It's learning the alphabet for chemistry, which is these guys. So if you've never had chemistry before, I'm going to show you how to get started. Memorize, not all. I'll tell you how many. In fact, one of the handouts has red boxes around the ones I want you to memorize. It's a periodic table. And the ones that I want you to memorize have red boxes around them. And the best way to do that is take a set of flashcards and just write the symbol on one side and the name on the other. And that starts the act of memorization. As you make the cards, it starts to sink in. And then you go and just run it. Anybody done flashcard memorization before? Yeah. And so you go through and you have a stack. You got those, you didn't get those, and you go back. You keep running until they're all in the good stack. Then you go back and do it again until you get them all. But you got to learn these. Otherwise, the rest of the semester would be a waste. Because we're going to do those, and then we're going to, let's see, into module 2. Let's see. We got module 2. Okay, so the first 2 chapters, we're going to learn these symbols. We're going to put the elements together in compounds, and we're going to name the compounds. And then we'll get into chapter 3 and 4. We'll get into actually talking about chemical reactions. Okay. I'm wandering again. Here's what the link will look like. This one, is that right here? You see this icon? So if I click on that, that would give me the exam 2, chapter 3 lecture part 1 that I conducted on the 6th of September last semester. Right, and they're still there. And what I'll do is, I think I have an archive folder down here. An archive folder. Yeah, archive videos. Once I replace those videos with current ones, I'll move the old ones into archives and still access them. Okay, so those are the PowerPoints, and then actually I slipped into module 2 while I'm doing this. I've got some other information here, and come to class, you get all these things in hard copy. I'll print them out for you, so you don't have to buy your own printer. Balancing chemical equations, these are helpful hints. View documents, useful information for your. This useful information is, you take your review document and look at the last pages. The last pages will be all useful information. Here, there, and you have the periodic table. On the exams, that useful information will be on the exam. You can count on it. So you don't have to memorize everything under the sun. But if you work enough problems and you use those formulas, you use the conversion factors and all of that other stuff enough, you're going to memorize it anyway. It's just unavoidable. So here's a review document, the PDF form. It's like the one I gave you. Then here's the review document key. So this is where you'll find the key in the same place right next to the review document. That's got all the answers, so you can check your stuff for that. And then the work problems are there also. Okay, and then after we get past archive videos, there should be practice tests. Right? If you like the electronic environment, you can go through and run these practice tests also. You don't have to have lockdown browser responders to do these. You just go straight into white space environment, and it will grade them for you, tell you which ones you missed, I won't see those grades. This is just practice. You can do it over and over and over again if you want. I wouldn't worry about these. These are instructors are giving these solutions. Not like liquid solutions. These are solutions to problems. For chapters 3 and chapter 4, in this case, at the end of the chapter. Okay, so this is what the exam would look like, and it looks like it's still up. But I wouldn't recommend taking it until you're ready. If I don't have the Respondus lockdown browser option available and you need to take the exam, and miss the exam day, then the paper exams are also PDF files in Brightspace. And what you would do is open it up. Most of them are fillable forms, right? So you open it up in your PDF reader, fill in, and it's set up so that you can save it. Right? I know most PDF files, when you put them in the reader, once you shut the reader down, you've lost all your work. But you can save these documents and submit them. Right? I'd rather you show them in person, because as people complete their exams and bring them to me, I grade them on the spot. So you know before you leave class what your grade is on it. There's no time lag in trying to figure out what you missed, what you're weak on, what you need to work on. Okay, any questions so far? Check to see if I missed anything. No, okay, we're good. So that's what each of the modules look like. And let's see, there's a fine module, but I don't think it has it. It just has a video review and okay. So what I'll do is I've prepared a review document for my purposes for the final exam. So I have something to guide me through, but it's really a compilation of all the others. Okay, so well, I got 30 minutes to do the first chapter. Let's see how fast I can move. Okay, so what I want to do now is open. Wait a minute. No, new copies. You can see my file structure. PowerPoint. Check it over. Slideshow. What you may notice, let me be in these front lights. I think it shows up better in the recording if I do that. I'll do my magic wand to get this. The printer. Okay. The textbook that you see, I think we're up to the 10th edition, if I'm not mistaken. Yeah, we're up to the 10th edition. So the cover will look different than this. And the borders and things in the pages and all the artwork will look a little different. But essentially, everything in here is in the textbook. I just don't feel like going back and using a new 10th edition set of slides and having to redo everything because they're extensively modified. All right, chemical foundations. Let's see, what do we mean by that? Well, first of all, what's chemistry? It's a pretty
It's a very broad definition. And it's the study of substances and how they change to other substances. So we're talking about identity, chemical identity. If the identity changes, then we have a chemical change. The identity of the substance doesn't change, it's physical. So, and to understand what's going on in chemistry, we have to think in terms of the microscopic world, at the atomic level. Sort of imagine yourself shrunk down to that size. And you're seeing things going on. What was that movie in the 70s? Fantastic Voyage, where they shrunk the people down and injected them into this guy to go make a repair or something. I don't know what it was. All I remember is it had Raquel Welch in it. So we observe at the macroscopic level what we see, what we can measure. But until very recently, we had to make certain assumptions and theorize about what was actually happening at the microscopic level, the atomic level. But if you can change your mindset to think in those terms, it will be helpful. All right, so we have atoms and molecules. We have tiny things. Where's the word atom come from? I like to break words apart because they do have meaning. I mean, in modern society, words don't mean as much as they used to. Right? Even in medieval times, or especially in ancient times, words had powerful meaning. And it was believed that if you spoke somebody's name, you had power over them. But the word means something. And in Greek, tome comes from the Greek word tomos, which means to cut or divide. And anything with an A prefix in the Greek format means not. So it means not cut. An atom can't be cut. It can't be made any smaller. You can't cut it. You have a pure element, and you start cutting it in halves and halves and halves. Eventually, you get down to the point where you have two atoms cut. You got two atoms, that's as far as you can go. No farther. Well, that's where the concept of the atom came from. And the concept of the atom actually goes way back to the Greeks, the ancient Greeks. Only they kind of got it wrong. They believed that everything was made of the same atom. So once you believe that, then you've got a whole lot of explaining to do about how things actually happen. It wasn't until the modern era that we actually figured it out. Anyway, you've got individual atoms that are characteristic of a particular element. In other words, they have physical and chemical properties that are unique to that element. So this element fluorine is a gas, and it reacts a certain way with other elements. It's very reactive with those metals on the far left-hand side, extremely reactive. But the element will have like billions of atoms. And then you can also have molecules. Molecules are collections of atoms that are bound together. They're bound so tightly that they behave as a single unit. So our example here is a water molecule. Right? That's an oxygen, and there are your two hydrogens. And they're bound so tightly, we'll discuss how that happens later, that they behave as a single unit. And they have a certain identity. Water at room temperature is a liquid. Right? And it has a tendency to dissolve certain things, and certain things it can't. Those behaviors are characteristic of water. Now, one thing you'll notice in this these elements that I want you to memorize, some of them have this blue highlight around it. Right? Hydrogen does, and then you have this upside down L. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine. those elements are in blue because at room temperature and 1 atmosphere pressure, they are all diatomic. In other words, they have 2 atoms bound very tightly together, right, into this molecule. That's the way they are when they enter any chemical reaction. So you need to know that, because if a word problem is presented to you and says, oxygen is reacted with hydrogen to produce water, write the equation. Right? If you just do this, it'll never work because it's not right. Oxygen is always diatomic. Hydrogen is always diatomic. Then you can balance your equation. Right, that's not balanced now, obviously. But we'll talk about how to do that later. So you need to know which ones of those are diatomic. Okay. Now you can react hydrogen and oxygen together and make water. Right? The space shuttle used to do it every time it blasted off. It had liquid oxygen and liquid hydrogen in that big orange tank on the outside. And that was responsible for the Challenger disaster. Right? One of the solid rocket boosters blew through its O-rings and punched a hole in that big orange tank and mixed the oxygen and hydrogen together uncontrollably and kablooey. So it's a very violent reaction when hydrogen and oxygen react to make water. That's why they use it in rocket fuel. But you can also go the other direction. If you take water and shove a direct current through it, then you can split the water molecule into hydrogen and oxygen. It's called electrolysis. Now, of course, pure water is an insulator, right? Low voltages will not pass through. So what you have to do is put something in there that will carry the charge, like just a little bit of acid to get the charge going, and then it'll split the water molecule. So this reaction can run backwards and forwards. It's just that when you put hydrogen and oxygen together, you get energy out. And when you want to split them apart, you got to put energy in. Right? And the same amount of energy you get out is the amount of energy you have to put in to make the split. Okay, let's talk about science a little bit. What does science mean? Well, we go back to our word analysis again. Science comes from a Greek word that in some contexts, it's translated as knowledge. And most people just stop there. But in other contexts, it means truth. So it goes a step beyond knowledge. Knowledge is basically just facts. And that's not bad. It's just that sometimes it doesn't tell the whole story. What we're trying to get at with science is, how does the natural world work? And particularly, how does it work with chemistry as its explainer? Well, we need a framework, and the scientific method is our framework. Now, the scientific method is a broad framework. In other words, it depends on what you're investigating. There are general ways to go from here to here to here, and it's very malleable, so that you can get answers from different fields of study. It's often called a plan of action. So your scientific method may be different for somebody that's graduated in my field, agronomy, crops and soils, versus somebody who spends all their time in the lab. It can be different. Field work requires a different set of steps. But overall, we're trying to get to the same knowledge. Not the same knowledge. Knowledge for a particular problem. And there's one characteristic about science that has been misused, I submit abused, especially by politicians and by bureaucrats. whenever you hear the phrase settled science, whoever has blurted that phrase out doesn't know what they're talking about. There's no such thing as settled science. There is agreed upon results of scientific investigations for a time, but it's never completely settled because science is open always to challenge. That's the good thing about science. So we don't have a dictator at the top telling you what to believe and you got to believe it or you're dead. In science, you experiment and you publish your results and you draw conclusions and you back up your conclusions with evidence, and then you have your peers look at it before it's even published. It's called peer review. And if you can get enough of them to agree in a magazine or a periodical to publish it for you, you're good to go. But then later down the road, you know, some aspiring young graduate student may take your work and try to reproduce your experiment. Can't do it. Right? So they may take issue with, they may call you up and say, how did you do this? Right? It says in the method you did it this way, but I can't get your results. Right? There's interchange and there's challenge. So you're free to challenge anybody's results. That's why when we set up our lab notebooks, I want them to be detailed enough so that you, at least you, can go back in the lab and repeat that experiment again using just your lab notebook. Keep that in the back of your mind. When you're writing things into your lab notebook, 6 months down the line, can I go back and understand what I just wrote? So if you've got somebody in your family or a friend who's interested, you know, have them read your book and see if they have a background in science in particular, they can tell you if it makes sense. And I'm going to give you some help. I'm not just going to throw books at you and say you're on your own. Right, so we'll get around to that in just a few minutes if I can ever stay on topic. Okay, so the scientific method generally and historically has started with an observation. Somebody was curious about something that was happening in nature, usually, and they wanted to explain something about that occurrence, that event. Well, with this observation, here's where the imagination comes in. You say, my hypothesis is that this happened because of these factors. And it produced those results. Okay. So you say, this is what I think happened. So you devise an experiment that will control lots of variables and leave only 1 or 2 variables open to change at will. That's the general design of an experiment. And then you look at the results and say, all right, do the results of this experiment support my hypothesis? I said this should happen because these are the conditions, initial conditions. And if it doesn't happen, then you don't throw it out, right? Negative results are not wasted. You just know, it's like Thomas Edison. What did he say? Somebody said, tell us about how you failed to make a light bulb 99 times. He says, I didn't fail. I made a light bulb. I only succeeded 1 time. Right? I had to try all those others to get to the success. Those are not his words, it's paraphrase. Anyway, so you can go in circles, right? Conduct the experiment, you evaluate it, and then you say, okay, well, let's see. Maybe I observe, or maybe I change my hypothesis and go back in and do another experiment. And you can just go in cycles like that. The job security. And then eventually, what you're going to come up with, and it doesn't show it on this slide. You have a copy of the slides there. Here we go. No, I'm missing something here. what you can derive from this is a law. And a law just simply relates what happens. Right? If you set out the conditions and the law states that when these conditions are operative, these will be the results. And if that works every time, then you've got a good go. Like, for instance, Robert Boyle, we'll study this one later. Robert Boyle said that if you hold everything else constant, if you hold temperature constant and you hold, that's my abbreviation for the number of moles. You haven't defined that yet, but that's the number of atoms or molecules that are in the container. It's a gas at this temperature now, and you change the pressure and observe the volume, then the pressure times the volume is always a constant value. That's a law, right? Or sometimes I use Isaac Newton. I mean, they're not chemistry problems, but anybody had physics in you? You've heard of Isaac Newton, right? Okay. He had 3 laws, right? The first law of motion was that anything in motion tends to stay in motion unless acted upon by an external force, or anything at rest tends to remain at rest unless acted upon by an external force. That's a law. And then his second law, he just said, mathematically, he said, F equals ma, force, mass, acceleration. He said, if you apply a force to this mass, it will accelerate that much. Right? It's a simple mathematical statement of his second law. And there are other laws. Like, I'm wasting time as it is, so I'm going to stop there. But eventually, if you repeat these experiments enough, you may come to feel like you understand why things are happening. And then you may want to propose a theory. Right? If you can explain, if you can say in your hypothesis why something is happening, and very often a model is created. It could be a mathematical model, it could be a physical model, like a toy airplane or a battleship, a model. It's not the real thing, it's a representation of the real thing. You can do that physically or mathematically. And the nice thing about models are that you can change the model. You can tweak it a little bit and still explain why something happens. If you make a prediction that you do an experiment and it doesn't give you the right prediction, then you can go back and tweak your model a little bit and try it again. Okay. Oh, this is good.
Until they tell me I'm violating some copyright. Oh, please. Can't play immediately. Don't live in my iPhone. From the 70s. Comedy group. Oh, it's a good one. I'll tell you what. I'll be sure and insert it in the recording. So you can go on Brightspace and look it up. Scroll down to this slide and watch the video. Oh, that's sad. That doesn't happen. Okay. So, this theory is the, I don't know if you call it the Holy Grail, but it's more powerful, more useful than laws, because laws have limited application. I mean, if you change anything in a law, then it doesn't work anymore. Right? But a theory is more malleable. All right, let's talk about measurements. I got 7 minutes left. In the lecture part, measurement implies a quantitative approach.
Quantitative versus qualitative. Let's do that first. The definition is embedded in the name. Quantitative means quantity. Right? It's like you can put a number to it. Quality is more like a feeling, or a nebulous observation, like the sky is blue. That's qualitative. The sky is blue because it transmits light at a frequency of, I don't know, 400 nanometers. That's quantitative. So when we do a measurement, get a quantitative measure, you've always got a number, like, I don't know, 12, and then you have a unit that goes with it, a scalar. Let's say 12 inches. Or how about this one? This is better. 70. Let me just put that up here. What does 70 mean? If I say I'm 70.
Nothing about measurement.
Yeah. I could be 70 years old. Not quite, but in February. Or I could be 70 inches tall. You got to have the measurement of the unit. And just parenthetically, when you do calculations with 2 or more measurements, you can't just throw the units out. The units enter the calculation also. You have to treat them along with the numbers. And we will do that. And the units sometimes can be compound. This one is joules times seconds. Or you can have miles per hour. Right? So the unit doesn't have to be singular. It can be compound. The compound units usually result from calculations anyway. Oops. That's the wrong button. Okay. Scientists have to have agreed upon units of measure. So when I say kilogram, every other scientist in the world knows what I mean. A mass is 1 kilogram. But we have a standard. Or when I say something is, I don't know, 2 meters long, they know, they understand what a meter means. It's fixed. So these are the fundamental units, SI units, which comes from a French word, system international, international system. And they're all what's known as metric units. Okay. So if you've never seen these before, the kilogram is the standard unit of mass. And since I'm running out of time, I'm not going to go into any details about that. They're described in your book, I'm sure. Length is the meter. Time is the second. Temperature is the Kelvin. Everybody understands what Celsius is. Kelvin is the same size unit as Celsius, only it starts at 0, a different 0 point. And we'll talk about that too. In fact, Kelvin starts at absolute 0. Electric current, we might use this one, maybe in the second semester we'll use amperes. Amount of something, a mole. A mole is just so many things. We're never going to do this one, candela, but it is a fundamental unit. Then everything else is a derived unit. These are standardized. They have standard objects, some of them, that represent the standard. The kilogram mass is like platinum iridium cylinder in a double bell jar with argon gas in there in some cave in France. Now, those units aren't necessarily easy to deal with, especially if you're looking at very large masses or very very large numbers or very small numbers. Sometimes you want to change the unit, derive a unit that's more useful. So we need prefixes. The kilo, look at this one right here. Kilo. Kilo means 1,000. So the abbreviation is K, and it's anything times 1,000. So actually the kilogram is 1,000 grams. But the gram is not the fundamental unit. The kilogram is the fundamental unit. So that might spin your head around it. The reason we went to kilogram as the standard unit is because the gram is too small. If you try to standardize the gram, if you're off by just say somebody gets a fingerprint on it, then that'll throw it off completely. But if you have a kilogram, then it's a little more forgiving percentage-wise. But it's based upon kilo being 1,000 times. Giga is 10 to the 9th billion. Mega is 10 to the 6th. I remember when a large hard drive was like 50 or 60 megabytes. It was like this, and weighed a ton, right? Now you can get terabytes in a drive that's, well, I've got one in there working now. It's like that form factor. We have 5 terabytes in that little form. Tera is, let's see, this is a billion, that's trillion. And then you can get up really big, peta. Just learn what these mean. Right? When you put those in front of a unit of measure, that multiplies the unit by that amount. We can go the other direction. We can make it smaller. So you can take the fundamental unit and stick these prefixes in front of it. Deci means 1/10 of. So a decimeter is 1/10 of a meter. So a meter's like that. Decimeter is about like that. Centimeter is 100th of, right? Centimeter is going to be maybe like that. So not quite, almost a half an inch. And then a millimeter, like 1,000th of. Micro, a millionth of, nano, a billionth of. Right? When they say nanotech, right? They're talking about technologies that are a billionth of a meter in size. Really tiny. So when you wear these modern sportswear, right, they're supposed to have nanotech in it. The fibers are on that scale. All right. So it's important to make this point. Mass and weight are not the same. They're related. You can't have weight without mass. So the difference is that mass is the same no matter where it is in the universe, as long as you're not relativistic. You're not going close to the speed of light or you're like near the black hole event horizon. Then mass is constant. Weight is a measure of force. And it all depends upon the gravitational field in which you find that mass. So on Earth, I may weigh 200 pounds. But on the moon, I'd be more like 35 pounds of force. So this is a topic that blows past a lot of students. An idea of uncertainty. I know if we had any lawyers in the room, they would just go apoplectic. Lawyers like certainty. Like they want expert witnesses on the stand. They can give them straight answers and answers that will win the case for them. But in the sciences, every measurement you make is uncertain. That means when you slap this number on the board, I don't know, 13.65, 4, whatever, we'll leave the units off for now. What does that mean? Well, it means that it might be 13.654, it might be 13.656 or 652. Like the last digit is always the uncertain. It's a guess. Sometimes it's a good guess, but it's always a guess. You can claim that these guys right here are certain, but the last one is the uncertain. And every scientist who reads data, numbers, reads them that way. The last number reported, the last digit, is the uncertain one. So you don't want to short yourself any information. You don't want to say 13.65 and stop when you meant to give it another digit because they're going to assume that that one's uncertain. Okay. It's an estimate. Now, what does that mean when you're in the lab? Well, if you're making a measurement and say you're making a measurement of length and you've got these markings on it for certain length and you've got the minor markings in here between them, but the object that you're measuring, right, comes in between these two marks right here. You can read certain up to this mark, but between these two marks is uncertain. Guess. Give us your best guess. That's what it means in practical terms. Okay. For example, this is a burette, right? Hopefully we'll get to use one of those, I think this semester. A burette is a device for dispensing liquid accurately. In other words, you measure, that's why it's numbered backwards, right? Small numbers are at the top, the larger ones at the bottom. Say if you start at 0 and you get down to this point, then you're down to 20, between 20 and 21, but there are 10 markings in between. So it's 20.1 and then halfway there. So 0.15, 20.15 would be that measurement. And that's how much liquid you delivered from the burette if you started from 0. If you started anywhere else, of course, you'd have to do by subtraction, right? Okay. There's your uncertain digit. Now, what's the difference between accuracy and precision? I've already used the term accuracy. Accuracy is how close is your measurement to the true value. That's a tall order because most of the time we don't know what the true value is. So we have to modify that. How close is your measurement to an accepted value? Okay. And then precision requires that you make 2 or more measurements. And then say, how close is the average of those values? How close are they each measurement to the average of the total? So if you have a wide spread out, you have like 2 here and 5 here and 10 there, you can get an average value from those, but they're spread way out. They're not precise. Okay. Now there are ways to express that. Like when you report a number, you could say 21.15, like on the previous slide, say plus or minus 0.01. So you're claiming that this last digit is good between 4 here and 6 here. Okay. And that would be a very precise number, right? If it's that close. Another way of representing accuracy and precision is with a dartboard. Right? So what's the accepted value? There's the bullseye. Okay. So if you've got averages of these darts close to the bullseye, like here, then you have an accurate value. Plus, they're all grouped very close together, so they're also precise. This one is precise, but it's not accurate because the average of these is nowhere near the bullseye. And this one is not precise and not accurate. There's one missing, isn't there? Not precise, but accurate. So if we had darts scattered like here, 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 like that, and the average was right there, you could claim that it was precise, the average is precise. Excuse me, the average is accurate, but not precise. All right. So now there are some rules. How do you deal with this problem of uncertainty? Well, when you write your number, there are, and you may have had this in math class already, significant figures. Have y'all talked about that? No? Okay, let's talk about it. Significant figures. So when you write a number, there are certain rules that tell you which numbers are significant. And the reason we're defining significant figures that way is because we're going to use that information in calculations. It has some value for standalone numbers, but it's more valuable for doing calculations when you add numbers together, when you multiply, divide. How many places can you claim in your answer based upon the calculation? Okay. So first of all, if all of the digits or any of the digits in your number are non-zero, they are significant. So this number has 4 significant figures in it. Then there's a problem with zeros. Right? There are 3 types of zeros. Zeros that are leading are never significant. The ones that are to the left, they don't count. They're just placeholders. I mean, you need them there, but as far as calculations go, they don't count. So this number has 2 significant figures. The zeros to the left don't count. And I will point out, I don't know how you learn to write decimal numbers, but if you write that number without that 0, it's wrong. You've got to have a leading 0 for a decimal. I call those orphan decimals. And I know grade school and even high school teachers teach it that way, but it's wrong. It's too easy to make a mistake if you have a decimal hanging out there. It looks like a period. Right? So always bracket your decimals with a 0. Okay, so that one had 2, right? That one had 2. Then you have captive zeros, those that are confined in between non-zero numbers. It could be 1 here, it could be 2, it could be 3 zeros in there, whatever the case may be. If they're bracketed by non-zero numbers, those zeros are significant because without them, it's not the same number. Okay, so we have 4 significant figures in this number. And then you'll never guess what the other flavor is. The right-hand 0. The right-hand zeros are dependent upon the decimal point. An explicit decimal point is required to make the zeros on the right-hand side significant. So this one, these 2 zeros are significant because that decimal right there. But this 0 is not significant because there's no explicit decimal. Now there's an understood decimal, yes. But for our counting purposes, that only has 2 significant figures. But what if you meant when you did the measurement to have 3 significant figures? All you got to do is put a decimal here. And the trailing zeros, that one has to hang by itself. Because if we have a 0 out there, you're claiming that other 0 is also significant, and that would be a lie. So that decimal rule only works for left-hand zeros. Okay. And then the last type of number is an exact number. This is a number that's not limited to any number of significant figures. And there are 2 types. One is one that we're going to use as a conversion factor. When you say 1 inch equals 2.5 centimeters, you're saying it's exactly that amount for calculation purposes. Or when you have counting types, like in this example, 9 pencils, right? 1/4 of a pencil doesn't make any sense. And when we write conversion factors, you can ignore the significant figures in the conversion factor in the calculation. Okay. So one way that we got around the problem of units of measure, where we have very large measurements to make a very small measurements, was to change the unit. But sometimes that's not good enough. Sometimes we have to write very large numbers or very small numbers in a new form, a notation, to sort of shrink them down, make them more manageable. Your textbook calls it exponential notation. But there's a difference between exponential notation and scientific notation. Exponential notation, all you need is a 10 with an exponent. So that 300 could be written like 30 times 10 to the 1. That's exponential. The scientific notation has to be written in such a way that this coefficient is between 1 and 10. And then you store up the movement of that decimal in your exponent. So if you move the decimal to the left, the coefficient gets smaller till you get the right size. And then when you move to the left, that's a positive increase in the exponent. Right? And all you have to do to prove it to yourself is just say, all right, what's 100 times 3 is 300. All right, okay, so yeah, we're right. If you had a number like this, right, you want to write that scientific notation, you would still move the decimal, but you go to the right this time. 1, 2, 3. So we have 3.00 because these are not significant, times 10. So should it be positive or negative exponent? Should be negative, right? Negative 3. Then all you have to do is multiply 1,000th times 3, and you get 3,000. Okay. You know you did right. Whenever you do a calculation or solve a problem, it's always a good idea as the last step to ask yourself if the answer makes sense. Right? If you're doing a calculation having to do with I don't know, some small occurrence, and your answer comes out in 35 billion, right? You may want to step back and take another look at your work. All right. So here are the rules for doing calculations based upon significant figures. You have two sets of rules. There's multiply, divide, add, subtract. Multiply, divide is the easy one. All you have to do is when you multiply or divide numbers, you can multiply or divide 2 numbers, 3 numbers, 4 numbers, doesn't matter. If all you're doing is multiplying and dividing, then you can do the whole calculation, and then you look back at the numbers that went into the calculation and say, which one has the least number of significant figures? That restricts your answer. In this case, 2 significant figures versus 4, the answer can only be 2. Now, as an intermediate step, you keep all your decimal points. I mean, all the places that your calculator spits out. That's okay. But when you report your answer, you have to round to 2 significant figures, right? And for rounding purposes, we're going to use the number 5 rule. Right? Anything less than 5, round down to the digit on the left of it. Anything 5 or greater, round up to the digit to the left of it. Oops, went backwards, sorry. There we go. Add, subtract is a little trickier. Add, subtract, we line up decimal points. So we're going to add 23.445 plus 7.83. We line up decimals, and we just add everything down. And then we say, we can only keep decimals of the least number of decimals in our numbers. So this one goes over there, we have to chop it off right here. And that means we round up, so it's 31.28. Okay. Now let's see if did I put that in? I had a what if that. No, I didn't. Okay, so let me do that. Suppose you have, I don't know, 23.445, and you want to add to that 210. What do? 5, 4, 4, 3, 3, 2. There's a decimal point. All right, where do you round it to? You can't round it to here because that one's not significant. So you got to round it to there. There. So your answer is 23. Okay, that's what you do when you don't have an explicit decimal point. Right? If we put a decimal point there, then you'd round it to this position. But in this case, you lined up the imaginary decimal point with the with the explicit decimal point, and then you're forced to ignore that one, and that limits your answer. It looks like I'm going to lose the battle of time. All right, when you're in the lab and you have to make measurements, multiple measurements, and combine them, what dictates the value or the accuracy of your final measurement? The least accurate device in the chain limits the accuracy. So in this case, we would be limited to the accuracy of this one. Right? So between 2 and 3, let's see, 1, 2, 3, 4, 5. So each one of these is 0.2. So it doesn't matter how accurate this one is. This one's going to limit it. Right? So you can only go down to the 10. Actually, you could only go down to 2/10. But I need to pick a different picture to make it easier to deal with. Okay, solving problems. What's my goal? In the real world, your curiosity leads to observations and questions about those observations. So the key is, what's the question? That's true for exams also. Right? What is the question? Or when you're in the lab, there's usually one principal thing you're getting at, one controlling principle for the entire lab. If we go in and want to measure the molar mass of some compound, right? That's your end goal. Right? That's the question. So what's the question? And then you say, all right, what do we know? Or what can we measure? And then you devise a way to get to the answer with what you know. That in general terms is problem solving. Dimensional analysis. In short, dimensional analysis is a way to do calculations, usually, by keeping track of the units of measure. And that very often involves conversion factors. So if I want to convert my height, which is 5 feet 11, into inches, then I need some sort of a conversion factor that will do that for me, to make the calculation. Or one example I like to use is, if I'm going to make a trip from here to Atlanta to visit relatives, where I can still have 2 sisters down there, I want to know how much money I need to carry with me to pay for the gas. So I need to know some things. The end question is, how much money? And the information I have is, what's the gas mileage on my car? How far is it? How much does gas cost? Right? And then you can use that information to get the answer for a one-way trip, double it for getting down there and back, and 10-15% for driving around. I don't know Atlanta, and make it 20%. And dimensional analysis is how we get there. We analyze the problem according to the dimensions, measurement, units of measure. Oops. Now these examples use the imperial system, the English system, but it works the same way no matter what. Now, when we need a conversion factor, in this case, we want to say a golfer putted a ball 6.8 feet across the green. How many inches did it travel? Well, we know that we have this 6.8 feet, and we want to end up with inches down here. So there's something in between that will get us from here to here. We know, mathematically speaking, that I can do this. I can multiply anything by 1. Right? That doesn't give us the answer. What we need is something to substitute for that 1. That's where equivalence comes in. So I know that 12 inches equals 1 foot. Okay. Now, if I divide this entire equation through by the same factor, that's permitted, correct? Mathematically, algebraically speaking. So what if I divide both sides through by 1 foot? There you go. That's equal to 1, isn't it? This is equal to 1. So instead of that, I'm going to put 12 inches equals 1 foot. Notice that this, when we write a number just off by itself or a unit, it's always considered to be in the numerator. The denominator is understood to be 1. So this is in the numerator, that's in the denominator. And remember, we calculate numbers and units. The units are in the numerator here, in the denominator there. They cancel. So 6.8 times 12. Anybody do that in your hand? Sometimes I can. Not today. 6.8 times 12 is 81.6. 81.6 inches. We get to keep this one because there's nothing to cancel it. So by analyzing the dimensions here and picking the right conversion factor, we got from this value and unit of measure to that value and unit of measure. Now let's be consistent. Right. This is a conversion factor. It's an exact number. It has no influence on significant figures. But this one only has 2 significant figures, right? So I'd have to round it, wouldn't it? 82 inches. Okay. And the nice thing about this conversion factors like this is that you can chain them together, right? If I wanted to go to some other unit instead of inches, then I need another factor that will cancel inches and leave me with the unit I want. So you can chain them as long as you want to go. Okay, but conversion factors work because all conversion factors are equal to 1. Let's see. All right, here we've chained them together. We want to go from pounds to grams. The conversion factor we know gets us from pounds to kilograms and then go from kilograms to grams. So the one you want to cancel, in the next one in the sequence, the unit has to go in the denominator. So we can cancel them. Because, and this is the thinking part of the solution, setting up the problem like that. After you get it set up correctly and you check your units to see if they're all going to cancel and give you the one you want, the rest is number crunching. Right? Anybody can do that. Okay. This example goes from New York to Los Angeles, right? Instead of from Beckley to Atlanta. But the same concept is involved, and I'm not going to spend a lot of time on that one right now because I don't have the time. Okay, various systems of measurement. One very important is temperature. And before we get into that, I want to classify the types of measurements you can make or the type of calculations that can result in values in terms of whether they are, they represent intrinsic or extrinsic properties. Intrinsic properties are those that don't change no matter how much of the substance there is, like density, so many grams per cubic centimeter, right? If you have this much gold, it has a certain density. If you have this much gold, yeah, it has the same density. But the mass of that gold is different because you have more amounts. So that's an extrinsic factor. Sometimes this is called an intensity factor, and this is a capacity factor. You might see it both ways. Temperature is an intrinsic or an intensity factor. In other words, the whole thing is at the same temperature, and you measure it. It's one of those properties that is intrinsic with a single unit. Most intrinsic factors are ratios, like grams per cubic centimeter. But this is one case where the unit of measure is an intensity factor. So we have basically three units of measure: Fahrenheit, Celsius, and Kelvin. The Celsius and Kelvin are closely related, and they're easiest to convert. Fahrenheit and Celsius take a little extra effort. But they all measure the same property, right? What's the average? I'm going to use the words we haven't defined yet. What's the average kinetic energy of the molecules or the atoms in that substance? That's what temperature measures, right? So the kinetic energy in the substance doesn't change when we measure it with Celsius or we measure it with Fahrenheit. So that's why you drive by a bank and they have the temperature flashing up on their billboard outside, and it'll say so many degrees Celsius, and then a few seconds later it'll flash Fahrenheit. Because they're measuring the same thing. The atmospheric temperature is just in different units. So that's why they're related, and that's why we can convert from one to the other. If you want to convert from Celsius temperature to Kelvin, you just say the Celsius temperature, whatever degrees Celsius, plus 273 equals whatever the temperature is in Kelvin. Right? Because of the same units of measure, we just move the 0 point by 273 degrees. Fahrenheit's a little different. If we want to convert Celsius and Fahrenheit, we need a different formula, which involves not only a multiplier, but an adder, an additive term. So if you know the Celsius temperature, we multiply it by 9/5, or in your book, it may say 1.8, same thing. Then you add 32 to it, that's Fahrenheit. So if you want to go from Fahrenheit to Kelvin, then you got to convert Fahrenheit to Celsius and then Celsius to Kelvin. And I memorized this one because, right, everybody had algebra. Okay, so you know how to manipulate unknowns. Okay, so we can resolve that one. We just say Fahrenheit minus 32 times 5 divided by 9 equals Celsius. Okay. So you can either do that, plug in your value here, or you can plug it in here and then solve for it. Either way works. Your book will probably say 273.15 or 17. We're not going to use those extras. Just use 273. That's good enough. And there are formulas. Oh, this is interesting. Since the size of the degree for Fahrenheit is smaller than the degree for Celsius, then at some point, if we draw their curves, their relationship curves, eventually it'll meet. So the value for Fahrenheit and Celsius will be the same. What temperature does that occur? Okay. Well, if Fahrenheit and Celsius are supposed to be equal in this scenario, then why don't we just change it? Make that X, make this X, right? And then solve for X, right? If you've got an equation with one unknown, you can solve it, right? So if we solve that equation, we find out that, let's see, here, yeah, we find out that at minus 40, Celsius degrees and Fahrenheit degrees are exactly equal. Right? Has anybody ever experienced minus 40? Has there been minus 40 here?
It was minus 40 up at Snowshoe not so long ago.
Where?
Up at Snowshoe.
Snowshoe. Okay. All right. Were you out in it?
I wasn't, but with my job, I meet people that did.
Okay. Yeah. So they know what it is. I used to work at minus 40 degree, a freezer at a hotel and restaurant supply in Atlanta. It was our blast freezer, and we used it to freeze various products we were producing, like hamburger patties, stuff like that. Roll them in there, and in a few minutes they were frozen solid. But once a month we had to do inventory. Right? And I was a low man on the totem pole. I was a student at the time, working part-time, so I didn't have any seniority. So I was the one that had to suit up and go in the blast freezer and take inventory. So I go in there for 10 or 15 minutes and come out into the cooler and warm up. But they were good to us. Before we went in, they fed us a nice big high calorie breakfast, sausage, and gravy, and biscuits, and, from our inventory, and it was good. Anyway, so much of that. It's cold. It is extremely cold. Okay, so we use density here to show you how formulas work. I mentioned one earlier was Newton's second law. This is more useful for us, density. Density is equal to mass of something divided by its volume. And that gives you a mass per unit volume. So it's an intensity factor. It's an intrinsic value. And the interesting thing about these types of formulas is, if you have two of these values, you can solve for the third one. It's just like any equation. If there's only one unknown, you're good to go. And I'm not going to throw any two unknowns at you. Right? How do you solve a two unknown equation? You don't unless you've got two equations, right? Two equations and two unknowns, you can solve them. We're not going to go that far. We'll just have equations and you'll have values, or you can find values for all but one of them, then solve it. So this can be solved in various ways. You can say mass equals density times volume, or volume equals mass divided by density, or which one didn't I do yet? Well, density mass divided by volume. And that gives you a unit of measure that's compounded, right? Grams per cubic centimeter in this case. And that's typical for solids. We report densities of solids in grams per cubic centimeter. And a cubic centimeter is like this, cubed on the inside. The interesting thing about it is a cubic centimeter is exactly the same as 1 milliliter. Anybody here in the health professions? You know what a milliliter is? It's about like that in a syringe. Right? Cubic centimeter and milliliter are exactly the same. So if you go into a hospital storage room and you find things listed as so many cc's, that's cubic centimeters. That's old stuff. Now they're labeling them as mLs. Little m, big L, because big L means liter and little m means milli. So 1,000th of a liter is a milliliter, which is also a cubic centimeter. All right, and this liquids are usually reported as grams per milliliter. So that's solids, that's liquids. How about gases? Gases are not very dense. So in order to make a measurement of a gas, you need more volume. So usually gases are reported as grams per liter. Okay, and there you are, solids, liquids, and gases. Those are the only phases of matter we're going to deal with. There are other phases, like plasma. Anybody ever gone in and had your muffler cut off with a plasma cutter? Those are fancy things. It's a high voltage charge through a stream of argon. And it just slices through that steel like a hot knife through butter. That's a different phase of matter. Yeah.
I wonder if it's a gas mass spec.
A gas mass spec? Oh, all right. Those are fun. But we're going to be concerned with solids, liquids, and gases primarily. Where can we find a plasma in nature? Surface of the sun. Yeah. And I think, well, this is not different. This is a solid. But I think that at the center of, or near the center of Jupiter, is the first liquid hydrogen and then solid hydrogen, because it's under such massive pressure. So you can get extremes in the universe, and we're not going to deal with those. This is what, remember I talked about thinking on the atomic level? This is what molecules of water would look like in the solid, liquid, and gas. So the gas molecules are far apart and moving very fast. The liquid molecules are very close together, but they're not in a regular order. There's not enough strength of attraction to hold them into a shape. That's why you have to put liquids in a vessel. They can maintain their own volume. They just can't hold their own shape. Solids can do both. They can hold their shape, they can hold their volume. Set them out on the desk, well, unless it's ice, and then of course it'll melt. But water is unusual. Notice that when water goes from liquid to solid, the molecules get farther apart because they go into this regular hexagonal structure. That's why snowflakes are six-sided. They're a macroscopic reflection of a microscopic arrangement of the molecules. And what that does is it opens up and leaves this empty space in here, this solid. What that does is it changes, it makes the solid less dense than the liquid. That's why ice floats in water, because it's not as dense as water. And it's a good thing too, right? What would happen if the temperature got cold and water were like a normal solid? It becomes more dense than the liquid, and it would just sink in every lake and ocean on the earth. And then the top layer would freeze again, it would sink, freeze again. Pretty soon the whole earth would be one solid ice cube. As it is though, water freezes and flows and provides insulation for the underlying layers. So that's a good thing. Okay, I'm not going to labor this too much. Solids are rigid, they have a fixed volume and fixed shape. Liquids don't hold their own shape. I mean, yeah, shape, but they do hold their volume. And gases don't hold either, because the molecules are so far apart. You have to confine them to maintain their volume. And when we talk about mixtures, a mixture is a combination of two or more substances in which the identity of each of those substances is maintained. It does not change in the mixture. There's no chemical reaction. Like one I use, I teach down at Logan on Fridays for Southern West Virginia Community College. And one of the experiments we do down there in a class is we separate sand and salt. So I have a mixture of sand and salt together, and they've got to go through a process to separate the two, weigh them, say how much is each. That's a mixture. I mean, the salt and the sand retain their identity through the whole process. Now, that mixture is heterogeneous. That is, when you sample, and that's one of the problems. When you sample that mixture, it depends on where you sample as to what percentage you get of each one. It's not uniform throughout. So the key is to mix it very well and take a large enough sample so that you minimize the error. Homogeneous mixtures, on the other hand, are uniform throughout. The composition, the percentage composition of each of the components is the same, no matter where you look. There's another name for homogeneous mixture. It's called solution. And the solutions can be a combination of all different phases. We normally think of combining a solid with a liquid like salt and water and make a solution, or sugar and water. But you can make a liquid solution, right? One type is called booze, alcohol and water. You can make solid solutions. Like some would call them alloys. Like brass is an alloy of zinc and copper primarily. Steel is an alloy of carbon and iron, and maybe some other additives. All right, I'm not going to stop at this one. We don't have time. Sorry. Physical change. A physical change is one in which the identity of the substance is unchanged. It can go through phase changes, like water. It's still water no matter what phase it's in. That's a physical change. And if you have a mixture in which the components do not react with one another, then you can use physical means to separate them. Right? If you have sand suspended in water, you can just filter it. Right? Or you can evaporate the water, and you're left behind with the sand. Or salt water. You can evaporate the water and you're left behind with salt. So I'm going to continue. This just means that you can separate these mixtures by physical means. Right? And there are various ways to do it. A chemical change requires a change in identity of the substance. So you can put natural gas on your stove. You can turn on the burner and natural gas comes out, mixes with air, oxygen in the air. And what you get when it burns is carbon dioxide and water, mostly. Like incomplete combustion will give you carbon monoxide, and that's what's so dangerous about gas burning. Right? Because carbon monoxide is, put it bluntly, it's fatal at certain levels. But the key is a change in identity. Chemical changes occur when the identity of the substances changes. I'm going to skip that one too, sorry. This is a decision tree, right? You've got matter, and is it a mixture or is it a pure substance? If it can't be separated into more than one pure substance, of course it's pure, right? Water is a compound that's a pure substance. Oxygen in a cylinder that people breathe is a pure substance. And you cannot separate the components of a pure substance except by chemical means. Right? We separated the components of water earlier with an electric current, and we made hydrogen and oxygen. That's the only way to separate pure substance components. If they're compound, if they're elements, then there's no separating. Right? You can break them down into atoms, but you can't make them into other substances, right? Except by nuclear means. Right? We're not going to do that because we don't have a nuclear reactor handy. Mixtures, on the other hand, you can separate them into various components by physical means. And they can either be heterogeneous or homogeneous mixtures, but the separation process is the same. Whichever one you choose will separate the components.